Hello friends, welcome to my YouTube channel Rajyam. In this video, I would like to give computational fluid dynamics analysis of flow over a square cylinder in two-dimensional. Okay. In last video, I explained about different steps involving in computational fluid dynamics CFD analysis, such as pre-processing, processing, and post-processing. Pre-processing is nothing but designing and meshing using different software, and processing is nothing but solver settings. Post processing is plotting and analyzing of results from the numerical simulation. So first we need to open the Gambit software for designing and meshing. So I will open one more time to understanding you. Gambit, this is very old meshing software. So CFD tutorial, then we need to select the corresponding folder for the meshing. So now the meshing module will come. In the meshing we have main three steps. One is designing and giving zone condition to the corresponding simulation model, and meshing. These are the three steps in meshing itself. So we can import the meshing model from the different CAD modeling software such as AutoCAD, Solid Edge, CATIA, Pro-E. We can import the model also. Otherwise we can create a model in Gambit also. So in this tutorial I am giving two-dimensional flow over a square cylinder. So I am creating a domain over here. Okay, first we need to create a square section, right? So I am creating a 1 unit of the square section. So in the x direction also 1, so y direction also 1, then so I created a square points, then we need to join the points, right? Okay, I created the square section. Then we need to have the bigger domain over here. So for that one I am making a bigger domain. So we will keep 10 dimensional in y direction and 20 dimension in x direction. So for this one we will keep this has a like 3D, like 3 surface, like 3 sides of the area, or 5 times we will keep. Here what we can do is, like, I created one, then in the x direction we will give -5, in the y direction we will give again -5. Here it will create a point. Similarly, so this point is not good, so we will give -10 over here. Okay, fine. And -5, then +5. Similarly, in the x direction I will keep 20. Okay, fit to window we can see bigger domain for this one. Similarly, in the y direction -5. Okay, I created the 4. This is the outer domain. Roughly I am taking this dimension, but we can keep proper calculation also. You can keep the domain based on proper calculation also. Right now I am keeping like small rough dimension for the understanding purpose. Okay, now I am creating the face. Okay, from the points, then points to lines, edges, then edges to faces. Okay, one module. This is outer domain model, and similarly we need to create a inner domain model also, right? So inner face. Okay, apply. I created this one. So we need to separate this inner part from the outer part. Here the face option will be there, separate option will be there, right? First we need to keep the bigger one, so I selected this and this as a this one. Okay, then apply. Okay, close. I separated the bigger, I separated the smaller square from the outer domain. Then like we can set the boundary conditions for this one domain. So this is inlet. Okay, velocity inlet, here velocity inlet, apply, show label and show color means we can clearly see the label name as well as the the name of the boundary condition. Here this is pressure outlet. Okay, then I am selecting here pressure outlet, then we will apply. Right, top surfaces we can keep in symmetric manner also, otherwise we will keep wall condition also. So I will keep wall for the both, right? Wall, right, apply. So wall, then we will select this all the module as square, right? That will also act as a wall because we are sending flow over a wall, so no need of inside domain, so we will keep that as a wall, right? Okay, then you apply. We can see 4 different square as a wall, and top and bottom as a wall, pressure outlet and velocity inlet, right? Okay, close. Then we will go to the mesh. Here how we can create the mesh is, we can create the face mesh, uniform meshes over all the faces. Okay, right, I'll select a single face only since we separated the inner square part from the bigger rectangular part, right? So we will keep a part as a interval part as a 1. No, what we will keep is we will keep 0.1, means it will create 10 divisions in 1 unit. Okay, right, then we will apply. It's creating a mesh. After mesh creation we need to export the .msh file for the Fluent software. Then we need to do the solver settings for our model. Okay, meshing is done. We will see how the mesh is. We can see all are like uniform meshes for the domain. Since this is like a very simple model, so we created the mesh also, right? Yeah, mesh looks good. Okay, we'll export the mesh. We need to select this option, enable this option. Then we need to set like 2D square, right? Okay, accept. The mesh was saved successfully. Then we will open the Fluent software for the solver setting. Okay, two-dimensional double precision. We will give the more accuracy because it will calculate more digits, like 16 digits it will take for the calculation, right? Okay, done. Then read the case or mesh, whatever it may be. So this one and square cylinder should mesh. Just a minute, I will rename this one 2D, right? 2D square mesh. We'll read this as a case or mesh. This is the older version, that's what it's showing, read case. In the newer version it will show us a read mesh. Okay, then we will check the grid, there any error is there. No, right now there is no error. We will check the statistics of the error. There is statistics of the cell sizes. So we have around 29,900 cells, right? So just we will do the mesh reordering. Okay, grid, right? Then reorder. Nowadays it will come as a mesh reorder domain. It will bring the QNS size to the 1, like bandwidth reduction is happened to the 1. So this will be useful for the like quick calculations. Then read and then grid check we did, and we'll check the scale. So it's showing in the meter, so it will take a long time to the calculation. Then we will see convert this into the mm, right, or cm, right? Okay, scale, close. Then we will check grid again. We will see the area minimum and maximum in meter. 0.12, so minus 0.12 plus 0.1 meter in x direction, y direction -5 to +5. That's the overall domain over here, right? So we did the meshing and importing the mesh, and grid checking also done. We need to define the module. Right, solver settings, two-dimensional. These are the basics. Pressure based solver we can use. This is not the supersonic flow. This is like subsonic only. These are the different options. This is not axis symmetric, this is 2D planar only, so we'll keep this as it is default. Then define materials, we will keep air itself, the same property of the air. We will send the flow over the square cylinder. Then we will go to the boundary condition. Here velocity set, we will keep 50 meter per second. Okay, this is for the simple calculation. Just for explaining to you, I am giving 50, right? Pressure outlet no need, no any changes here. Only we can set the velocity, right? Then we define the boundary condition also. In this one nothing is there. Then solver control, so it will also like we will keep as it is. We are not doing much more research over here, just we are doing some understanding of the flow over a square cylinder, and this tutorial will be very useful for the beginners, right? So solve also done. Then initialization from the velocity inlet, right? X, apply initializations, close, right? Okay, done. Then remaining stuff no need right now. Then we will go to write and auto save. Auto save is like every every, let's take 50. Okay. To keep 100. Okay. Okay, sorry, this will keep 1000, but here we can keep 100. Means for every 1000 time step it will save the case, remaining it will save the data, it will save for the 100. Okay, done. For safety point of view, we'll save the, write the case and data, right? Okay, dot gz, I will give underscore start, right? I'm saving the initial conditions for the future reference. So we will go to the solver, iterate. Okay, number of iterations we'll keep thousands. Okay, apply, iterate. Iteration started. So I will pass here. So after 1000 iteration it stop, because we given the conditions up to 1000 iterations. We'll see the post processing of the last case and data, then how it look like. Then if needed we will proceed further. Okay, then I'm doing the post processing in the TechPlot software. So I'm opening TechPlot software for post processing. So it's loading. Yeah, it's loading. So I will read the like 1000 data and initial case, or like 100 case will take. Then we'll see how it's look like in. If needed further we will run the simulations. Just this and all, just for understanding purpose. If you want to improve the quality of the simulations, we need to do many parameters such as grid convergence study and entrance length calculations and meshing, quality meshing. We need to capture very accurately, means we need to increase the cells nearer the body, inflation method. We have the different options to do that one. In the later videos I will explain. These are just for understanding purpose for you and learning purpose only. Okay, uh, so case and data, right? Sorry, you are correct folder only. So 1000 case, 1000 data. I am opening over here. So it's opened. Here we can see. First I will set the domain like the proper way. So tick we will keep as outside. That will be looking good. Oh, sorry, we also outside. And line we will keep the border line also, right? So in the range x is fine. Y we need to change minus 0.5, sorry, 0.5 to plus 0.5, 0.5, right? I made a mistake, small mistake over here, right? Just a minute. View data fit. Okay, the y directions 5 and this one also 0.05, right? Yeah, so we created the proper domain. Contour, this is a pressure contour. I can see where the pressure is more. We will see the velocity magnitude in x direction. So this is the x direction velocity of the square cylinder. For the clear understanding point, we will set the number of increment is more, like 21. We will see the many regime like of the plot. For this one we will keep as automatic regime. This is the x velocity, and similarly I will calculate the velocity, calculate variables, and I will calculate the velocity over here. Velocity magnitude will calculate based on the x velocity as well as the y velocity. So let's see the contour of the velocity magnitude, right? Yeah, this is how the velocity magnitude will be there. Here we can see the bigger at, I will zoom the area at, this is stagnant point where the velocity brings to the zero, we can see clearly. And similarly at the, this is leading edge, this is trailing edge. Trailing edge of the square, it's having the back pressure. So back pressure means it's having the low regime of the pressure, and as well as low regime of velocity. We'll keep as a data weight, right? Okay, then I will export this to a proper, okay, we will keep the contour in horizontal manner, that will look like a, right? Yeah, okay. Here we can change the number also. Here the regime at 21 I will keep. Let's start from 0, right? Yeah, this is the velocity contour. I am exporting this velocity contour into the corresponding folder. So here we can do some more fine tune work also to look better, right? Legend, this I will remove. Text color, automatic, the color box, color bar, and header. Header we can keep, and cut off. These are the different stuff. Legend box, right? We will keep without no box here. Then we will skip this one. We will manually add the insert text here. Then here we can keep velocity magnitude. Velocity, just we will keep velocity, then unit meter per second. Okay, right, accept. Here we can move wherever we want this one. Okay, we can bring closer to this contour, legend, color bar. Then this is okay. Suppose we need to show at which time this plot is, right? For this one again we need to insert the text here, the time, solution time or time, let it be time, let it be time here. Bracket and symbol and solution time. Accept. So this is showing 0, means like it is taking 3 digit only. So we'll delete this one, as of now no need, right? Yeah, this is how we can do the overall. Why it's showing only 0 means this is not related to the time dependent problem. So this is a steady state problem, that's what it's showing, the time is 0. So no need time for this type of steady state problem. Let it be, we will export the quality, enter width. So I am exporting high quality, let's say 1500. I will export the TIFF will be good. So based on your requirement you can import or export the images. So I'm exporting in the PNG format right now, in the floor square cylinder. So velocity contour, right? Similarly you can export different contours such as pressure, and what is your requirement you can export the stuff. And here I am going to show the velocity vector over here. uh, uh, so contour will remove. Here we can see the clear what the arrow mark of the vector. So this is a simple procedure I am explaining how to do the vector. Here we can see it's coming and it's going there. So here insert plot in the vector. We can change whatever you want. You can change arrowhead or reference vector like that. Then again I will show the streamline. I will switch off the vector, then I will show the streamline. Before that I will data fit. So we'll draw the streamline. Like just you select the mouse and you drag it down, so it will plot over here. See how nicely it's coming. Similarly I am doing one more time here, then it will add some more points here, right? So here we can see how the flow is streamlined is there behind the square cavity. So if you want this also we can export like streamline or a yeah streamline. Simply I'm exporting streamline. Okay, right? Yeah. So I will finish this video. I will stop this video now. If you want more videos, if you have any doubt, please comment me in the comment section. Thank you for watching. Thank you.